Hey, what's up, guys? This is Cheng here. So this time, let's take a look at this one. Okay, 1,819. Number of different subsequences, GCDs. Okay, so you're given like an array numbers, right, and consist of positive integers, and your task is to return basically the number of different GCDs among all the non-empty subsequences of nums. So the GCDs, of course, you guys all know that it's a greatest common divisor, right? So for example, the GCD of this 4, 6, 16 is 2, right? It's a greatest common divisor. And our task, we need to find all the subsequences, the distinct value of the GCDs among all the subsequences. So for example, we have this nums here, right? So the length of 3, so in example 1 here, we list all the possible subsequences. And then here are the corresponding GCDs for each subsequence. And in the end, we have 5 distinct GCD values. That's why the output is 5, right? And here's another one. And the constraint is like this: 10 to the power of 5, right? So I mean, at the beginning, right? So if we follow the examples or follow the description of this problem, by calculating a GCD for a subsequence, then we need to basically loop through all the subsequence of this problem. And given this kind of constraints, it will definitely TLE, right? Because the subsequence is like a combination, right? Well, yes, like combination of all this kind of each of the entire numbers, which will be too large to be enumerate, right? So that's why we have to somehow figure out a different way, a different strategy to solve this problem. And to be able to do it, we have to be able to make some observations, or we have to know some of the characteristics of the GCDs. So the first thing is this. So given like the range of the numbers, so the biggest number is 2 times 10 to the power of 5. So what does this one tells us? It tells us the range of the distinct value of GCD is from 1 to this 2 to the power of 5, right? Because the GCD can never be greater than the number itself. That's a fact, right? So which means that with this given range, I think we can just actually enumerate each possible GCD value, right? And then we check with that GCD value, given that GCD value, can we find a subsequence? Can we find a subsequence that can have a GCD of that value? And if that's true, and then we simply increase the answer by 1, right? For that specific GCD value. So now the problem comes down to, given like a GCD value x, let's say, right? Given x as GCD, as GCD value, right? How can we find a subsequence that has this value x as a GCD, right? So to do this, we also need to make some observations again. So first, the possible subsequence, or the possible numbers that can form this x as a GCD it must be the multiple of x. So what does this one mean? It means that, let's say, for example, if x equals to 4, I'm just using this as an example, right? So the possible GCDs, the possible subsequence that can have this 4 as a GCD is what? It's a 4, 8, 12, 16, 20, 24, and then so on and so forth until the limit of here. So this is kind of obvious, right? Because only then we could possibly find like a subsequence from here whose GCD is 4. Otherwise, if we have like a 9 here, that 9 definitely will not give us like a 4, because the GCD, what is GCD? It's a divisor, right? So divisor means that we have to be able to find to be divided, right? That number has to be dividable by this x here. That's why the potential candidates of the numbers are all the multiple of this x value here. So that's the first observation. And the second one, given this kind of like possible candidates, and the GCD, depending on which numbers which number we're picking here, the possible GCD values of that any subsequence can only be either greater than x or equal than x. And so this is also kind of not too hard to realize that, because let's say x is 4, right? So no matter which number we pick, no matter which number we pick from this candidate here, how many numbers we pick, the GCD will at least be 4, right? Let's say if we pick 8 and 16, right? So obviously, for 8 and 16, the GCD for these two numbers is 8, right? 8 is greater than 4, right? But if we pick the 8 and 12, right? So then the GCD of these two numbers is what? Is 4, right? So given like this kind of the multiple of this GCD here, depending on which what are the subsequence we pick, right? Which numbers we include into our subsequence, the GCD will only be either greater than x or equal to x. And the last observation is that the more numbers we include into our subsequence, the smaller the GCD will become. Okay, so what does that mean? Let's say we have 20 and 40, right? So at the beginning, let's say we only pick these two numbers. Obviously, the current GCD of these two numbers is what? Is 20, right? Now, if we include more numbers, it did include more numbers from this, of course, from this kind of candidates list here. The GCD will only going down. So let's say we pick 10. Sorry, not 10 actually. Let's say if we add 80, if we add 60 here, right? So by adding a 60 here, actually the GCD will stay as 20, right? Basically, it will not decrease. But if we add let's say 16 in this case, yeah, if we add like 16 here, I believe this. If we include 16 here, so the GCD for this one, it's gonna be actually, so yeah, if we add this one, the GCD will become to 4 in this case. Right. Yeah. Yeah. So this is basically that's the another like uh fact that the more values we include from this candidates list, the smaller the GCD will become, and the smallest it can get is the x itself, right? So then, okay, we find like a solution already. Basically, for each of the x here, we'll get all the candidates of this x, which is the multiple of x from the x itself to the limits, and then we'll try to build the GCD. We'll try to include those numbers one by one. Of course, we also need to check if this like number exists in this number itself, right? So if it exists, then we'll try to include that include that number into our subsequence, and we'll try to calculate the GCD for all those kind of the worst case scenario is that we have to basically include each number into our subsequence, and then we'll see if we can find like the GCD equals to X, because like I said, the more numbers we include into our GCD, the smaller the GCD will become, right? So basically, so what it means that if we have include all the numbers from this candidates list, and the GCD is still greater than X, then it means that we cannot find a subsequence from this nums whose GCD is equal to X, right? Cool. So I think that's the logic. And so if we have find the logic here, actually the coding is pretty simple. So first, we need to find the limit, right? So for the limit, actually we can do this. So we don't have to use this. We can either use 10 to the power of 5, or we can just do a max of number of the nums here, right? Yeah. So basically, we're getting the max number because that's going to be the limit, the upper bound of the GCD values, right? And then, like I said, to be able to find if the number exists in this nums here, we're also gonna create like a num stat, right? So that the check can be a O1 time, okay? And then we have answer equal to 0, right? And then we have I in range of 1 to max plus 1, right? So that's gonna be the check range for each GCD value, okay? And to calculate the GCD for a subsequence, I think this is kind of also kind of obvious, because let's say we try to include the numbers for 4, 8, and 12, right? So first we'll calculate the GCD for this two, So the GCD of this three numbers equals to the GCD of the first two numbers, right? The GCD of the first two numbers, and then for the third one, we can simply do another GCD on the result of the first GCD plus the card number. That's going to be the GCD, right, of the three numbers. Because the first one is 4, so 4 of GCD of 12 also equals to 4, right? That's how we calculate this GCD. Okay, so now, which means that I can just do a current GCD here, right? We start from 0, and this is going to be X, right? So, and then for each number in the range of the X we need to find all the multiple of X, right? And the max plus 1, and then the step will be X itself, right? That's how we find all the multiple of the current X within the range, and then we check if number is in the num set, right? So if this one exists in the current nums here, we're gonna update our current GCD equals to GCD of current GCD of num, right? Like I said, so the more numbers we include into this into our current GCD, the smaller it will become. Basically, it will only going down, and the smallest it can get is the X itself. So we can have like simple, we can do an early termination. Basically, if the current GCD is equal to the X, right, then we increase the answer by 1, and then we do a break. Or we don't have to do this, or we just simply find all the possible multiple numbers in this nums here, and we just do a GCD among all of them. Because like I said, the smallest it can get is X itself if we include all the numbers, right? So if in the end it still cannot find the GCD, if in the end the GCD doesn't equal to X, then we'll simply just ignore it. We'll simply not increase that. So here it's just like early termination, or we can just do. So let me or we can just in the end we do this, right? So if the current GCD is equal to x, right, and then I increase the answer by 1. This is the same thing, right? Here is just like a little bit of termination, because since it's only going down, and as long as it has reached the number itself, we know, okay, we don't need to include more numbers, because we have find the smallest number that GCD could ever get, right? Yeah, so that's the basic idea. So for the GCD, you can implement yourself, right? So the GCD is very kind of straightforward. Basically, we have A and B here, right? So while B, this is a template basically, and then we do A equals to AB equals to the B, and then A modular by B, right? And then in the end, we return A. That's it. So the reason I include this current GCD defined as 0 is because with GCD 0 to any numbers, so 0 GCD 0 and any number x, the value is x itself, right? So you can you can just verify it. So if A is 0, B is x, so B is not empty, So the B will be or x will become to A, and the B will become to 0. So that's why we just stop. We return A. So if B is 0 and A is x, we simply will not enter this while loop, and we simply return the A itself, right? That's because at the beginning, if there's no GCD at all, right? I mean, the current GCD will be the number itself. That's why we define the current GCD starting at 0 as the initial value. Cool. I think that's it, right? So now we just run the code. I think current. Oh, I think there's a typo here. Current. Yes, current. So accept it, right? If I submit. Yeah. So it passed, right? So the reason it passed is because the time complexity. So what's the time complexity for this? So at the beginning, at the very outer loop, we have like n here, right? Assuming n is the 10 to the power of 5, right? And outer loop is n, and for the inner loop is, so this one is a little bit tricky, because for each number, depending on the number itself, right? I mean, depending on the number, so here it's more like a log n, because for when the one when the x equals to 1, right, here it will be n itself, right? And then when the x equals to 2, it's gonna be n divided by 2, right? So when the x equal to 3, the number of the inner for loop will be n divided by 3, so on and so forth. So this one is close to what? It's close to n log n, actually, right? N log n, and that's going to be the two loops time complexity. And for this GCD here, I think for GCD we someone think this GCD is O of 1. Someone think this one is a log n, because here, as you guys can see, it also basically do a modular of while. So this one is also similar with a log n. So depending on how we measure this GCD function itself, so it could be at base we have n log n. So here we have another log n based on this GCD function here. Yep, I think that's it for this problem, right? I mean, it's a pure math problem, to solve this one, we have to know some characteristics and facts regarding the GCDs, like the only possible. So the first one, like I said, the first, for given like a GCD here, the possible numbers that can have this x as a GCD is like the multiple of this x here. And the second one is so the more values, the more numbers we include into our current subsequence, the smaller the GCD becomes. And the GCD can only be as small as the x itself, right? If we are like trying to find the among all the multiple of the x here. And then, yeah, there you go. Cool. I would stop here and thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.